The law of total probability can be used to compute the probability of an event conditioned on other events, but it can also be used to find conditional probabilities. A key strategy: everything comes from somewhere, everything goes to somewhere. So, let's suppose a salesperson covers two territories, X and Y. 30% of their customers will buy nothing, 25% of those in territory X buy nothing, while 40% of those in territory Y buy nothing. Suppose a person buys nothing. What's the probability they were from territory X? So let N be the event a person buys nothing, X the event they are from territory X, and Y the event they're from territory Y. So we're given the probability they buy nothing, the probability they buy nothing given that they're from X, and given that they're from Y. Now, we want to find the probability that they're from X given that they buy nothing, and we can use Bayes' theorem, except we don't know the probability they're from X. But now consider our law of total probability. The probability they buy nothing, well, they either came from territory X or territory Y, and so we can set that up. And since every customer is either from X or Y, then if the probability they're from X is P, the probability they're from Y is 1 minus P. And so we can set up our equation and solve. And so we find the probability that they're from territory X. And now we can substitute our values into Bayes' theorem. We can also use the law of total probability to solve some problems that we solved other ways. So let's consider the hat problem, for people check their hats at the beginning of an event. When they leave, they're randomly given one hat. What's the probability no one receives their original hat? So remember, you can always list. Sometimes it's not convenient, but in this case, the problem is small enough that we could do so. If we designate the hats of persons 1, 2, 3, and 4 as A, B, C, and D, there are 4 factorial 24 ways the hats could be returned. Of these ways, the first person does not get their hat back if they receive hat B, C, or D. So suppose they get hat B. Then the only way for nobody else to get their hats back is for the hats to be distributed as BADC, BDAC, or BCDA. We'd get a similar set of outcomes if they received hat C or D. And so there are 9 ways where nobody gets their own hat back, for a probability of 9/24, 0.375. So again, if you really want to understand a math problem, solve it again. So let's consider the complement where at least one person gets their own hat back. So suppose the first person gets hat A, their own hat. The remaining hats can be distributed in 3 factorial 6 ways, all of which result in at least the first person getting their own hat. But if the first person gets hat B, then there are 3 ways in which at least one person gets their hat back. With analogous outcomes if they get hat C or D. So there are 9 more ways that at least one person can get their own hat back. And so there's 6 plus 9, 15 ways at least one person gets their own hat back. And so 24 minus 15, 9 ways that nobody gets their hat back. So the probability no one gets their hat back is 9/24, again, 0.375. So now let's use the law of total probability. Let A be the event that the first person gets hat A, so they get their own hat back, and R the event that at least one person gets their own hat back. So the probability of A is 1/4, and so the probability of R given A is a certainty. The probability of a complement is going to be 3/4. How about the probability of R given a complement? So if the first person doesn't get their own hat back, probability 3/4, there are 6 ways of returning the remaining hats. So suppose the first person got the B hat. The only way for at least one person to get their hat back is for the last 3 hats to be distributed in one of 3 ways out of 6 possible permutations. So the probability that at least one person will get their hat back, given that the first person did not, is 1/2. And it's important to note that this is the probability regardless of which hat the person actually got. So the probability of R, given the first person did not get their hat back, is going to be 1/2. Our law of total probability says the probability of R is and remember, that's the probability that at least one person got their hat back. So the probability nobody did is, once again, 3/8.